I am going to talk about Kloosterman sums, and this is a joint project I did with Maki Nakasuji. This was from my previous job, actually, not from Riemann, but she's from Sophia University, and I was in a JSPS fellowship. Maybe I should mention that a little bit, maybe if any of you are interested. So that's government, or like buranın TÜBİTAğı fellowship. That the aim is to get foreigners. It's only aimed at foreigners working with a professor from a Japanese institution. So you have a host here, and you apply together. And the aim is so that the Japanese mathematics or other fields are not insular. Like there's intermingling of ideas. Okay, so I'm going to talk about Kloosterman sums, and the SL3 Kloosterman sum. What we did is write a formula for SL3 Kloosterman sum, but let me first introduce what is the classical Kloosterman sum. And by the way, for those of you who were at the Boğaziçi talk, this is like from that time. This is a work from last year, so there will be repetition. So this is the Kloosterman sum, the classical one. It's a finite sum. It's an exponential sum. So here EZ is e to the 2 pi I z. Can you all see my cursor? Okumu görebiliyor musunuz mouse'umu?
Sanıyorum evet.
Tamam. So I'll be using that to point at stuff. So here EZ is e to the 2 pi I z. So these are all points on the complex unit circle. And there's a single parameter. Well, it looks like there's two, but like one of them is the inverse of each other. And this is summing over all A modulo C. Well, this condition is making sure that, well, this necessitates that A and C are relatively prime to each other. And this is the Kloosterman sum modulo C with two twisting parameters, M and N. So I said I'm going to talk about SL3 Kloosterman sums, and my claim is that this is the SL2 Kloosterman sum. And SL2 is like 2 by 2 matrices with determinant 1. And the point is, like, first I have to make sure that I need to convince you that this has to do something to do with matrices. At the present, there is nothing that says matrices here. It's a finite exponential sum. And our goal is to write the SL3 Kloosterman sum as understandably as this one. So this is the level we're aiming at, because there's like a finite parameter. And using that, we would be able to have an expansion for the triple divisor function. So that is the number of ways of writing n as a product of 3 integers, or variants thereof. We will be able to have like an infinite Dirichlet series expansion for this arithmetic function, which will be useful in, which could be useful in understanding moments of the Riemann zeta function. And on that note, well, you saw the second slide. I'm going to talk about the Riemann zeta function. This will be like a interlude, quite a long one, about the Riemann zeta function. Any questions up to this point? Okay, at any point, if you have questions, please do interrupt and ask. So the Riemann zeta function is given as a Dirichlet series. It's written like that. It has a Euler product. This is called the Euler product expansion. So this is a manifestation of the fact that the integers have, the positive integers have a unique prime factorization. So every n here can be written as a product of powers of primes. This is how you sum the geometric sum series. Anyway, it has a completion, a so-called completion. So basically the heuristic here is that, or the idea here is that This Riemann zeta function is a product over all primes, and there's one prime at infinity. And that to include that in the Euler product, you include the gamma factor. So the gamma function is, this is the gamma function you might already be familiar with. This is a generalization of the factorial function onto the complex plane. So this is gamma n is like all the numbers from 1 to n minus 1 multiplied, the factorial function, the holomorphic one. So once you do this completion, it is a symmetric, it has a functional equation. Zeta star s is equal to zeta star 1 minus s. And with that, we understand it in more, in a larger region. So the Riemann zeta function itself is, well, these series, both the product and the Divisor series converge only for real part of s greater than 1. So, for example, from the product expansion, we know that there are no, the zeta s doesn't take the value 0 at any point in this region, in this gray region. From the functional equation, we understand the values of the Riemann zeta function on the left half plane with real part of s less than 0 from this one that I just wrote. So we understand the values. For example, we understand that, I mean, there are zeros of the Riemann zeta function here, but we understand where they are. So every negative even integer, for example, we understand that there's a, they're there. The middle region, this strip, is more mysterious. And this was, so the Riemann zeta function was introduced earlier, but Riemann was, I think, the first person to consider it as a function of the complex plane. And he conjectured that for there are no zeros of the Riemann zeta function to the right of the middle of this question mark realm. Okay, so that is the Riemann zeta function and that is the Riemann hypothesis. And there are some things we want to do with understand the Riemann zeta function. So a common thing we do is try to look at, these are called the moments of the Riemann zeta function. So there are very detailed conjectures on what the moments, so these are powers of the Riemann zeta function at the center of this question mark realm, trying to understand how fast these values grow. This would be a way of measuring it. So for example, if there's a very high value of the zeta 1/2 plus it, you would see it if you raise it to a large power. But the conjecture is that it doesn't grow very much, at least on average. So this is what we have is a polynomial of the logarithm of t. So t times, so you're integrating something from 0 to t. So the size of that should be t if the Riemann zeta function was 1 everywhere. But it does oscillate a little bit, and then you're raising it to higher powers. So you do gain a little bit more. You'd gain a power of log t. And we do understand this polynomial, like the first term, the second term. I mean, when I say we understand, we have very explicit conjectures about what this polynomial should be. But in terms of proofs, there's very little known. Oh, sorry, the other way. So Hardy and Littlewood in 1916, in the middle of the war, proved that the second power of the Riemann zeta function was the second moment, as it's called, is t log t, is asymptotic to t log t as t goes off to infinity. 10 years later, Ingham proved that the fourth moment is asymptotic. Right now we know much more. Like, for example, right now we know that it's asymptotic. The first one is asymptotic to t log t plus a constant term times t plus an error term that has a savings of t to the power, where the power is less than 1. But these are the first terms in the asymptotic. And Ingham proved that the in the fourth moment, it's asymptotic to t log to the 4t. And beyond this, the next one would be the sixth moment. Well, maybe the fifth, you might think, but it behaves much better when when they're even. So we consider them 2 by 2. So the next one would be t to the is the sixth moment, but nothing like an asymptotic is known, but not even we don't even know that the sixth moment behaves Lindelof on average. And I'll mention what it means to be Lindelof on average. We don't know, like it grows like this sixth moment is t to the 1 plus epsilon at the order of t to the 1 plus epsilon. So, I mean, forget there are conjectures. We know that it should be a constant times t log to the 9th power t, but we don't know this. So maybe let me mention Lindelof for a short while. This is Lindelof. He was a Finnish mathematician. His father was also a mathematician. And this is his paper on where he mentions on some remarks on the growth of the function zeta. This paper he actually published in the same year his father died. So this is the part where he talks about Riemann hypothesis. So the idea is that if you do assume the Riemann hypothesis, then the Riemann zeta function grows this much. Is the conclusion from here. This is the Riemann hypothesis.
What is that, Mehmet?
What is sorry?
What is the less than symbol with epsilon?
Oh, yes. Thank you very much. Thank you. So less than epsilon, less than sub epsilon means, and I should have written that, but I didn't. This is a very common symbol in analytic number theory. It means it's less than or equal to the left-hand side, absolute. So first of all, it means that absolute value of the Riemann zeta function 1/2 plus it is less than or equal to a constant times 1 plus t to the power epsilon. And the constant may depend on epsilon, will depend on epsilon. So it's c sub epsilon is what that means. So it's less than a constant times the right-hand side. The left-hand side in absolute values is less than or equal to a constant which depends on epsilon times the right-hand side is the meaning of the symbol.
Thank
you for asking. So I said the Riemann zeta. So this is why moments. So this is why we would expect the moments of the Riemann zeta function here to be small. It doesn't mean that we would expect the exact form of these, like t log to the 9 or anything like that, but we would expect them to be at the order of t to the 1 plus epsilon, if it were satisfied. So why would the Riemann zeta function have anything to do with the divisor function? So I'll mention that the Riemann zeta function, let's take 2 of them. So instead of like a second power, we can do take 2 with s and w. We can take s and w to be the same afterwards. Bring the sums together. Make them to the same exponent. So put m1 times m2 equals n. And then the inside is a summation, a finite sum over divisors of n. Let's call that the inside, the inner sum, sigma. So here sigma is the divisor sum function. And this is exactly what that is, the sigma of s minus w. And so notice that I made a quick jump there. So maybe back and there again. So this is zeta squared. If you take s equals w, maybe a little back again. So if you take s equals w, what you are measuring is zeta sigma of 0 of n. So if S is 0, then you're just counting the number of divisors. So that we can call D2. So that's the number of ways of writing it as a product of two integers. So zeta squared would be a Dirichlet series where we can write D2 of n over n to the s. Why would this be useful? Well, in the study of moments, this would be useful in the study of moments because, for example, take the fourth moment. You can separate that into two parts, and this is the reason why we would want even powers, into the zeta 1/2 plus it squared and zeta 1/2 minus it squared. And the next step would be is to try to express the Riemann zeta function squared in terms of D2 summation of D2n, and the other one as well, and then go on from there. I'm not going to do anything else more, but there are proofs of what Ingham has done using this idea, where the starting point is first separating the zetas into two parts, and then writing it in terms of the divisor function, the number of divisors. And then write the number of divisors. So what do you do? So you have two numbers of divisors, D2 of n, D2 of m. Let's say like one of them is D2 of n, the other one is D2 of m. At that point, you want to do something. And the thing you can do is, well, one thing you can do, and this is how some of the proofs go, is express the divisor function, the divisor sum function, as a Dirichlet series of, well, these are called Ramanujan sums, but they're a special case of Kloosterman sums. So this is the Ramanujan sum. The reason it's expressed here is that I'm talking about Kloosterman sums, and this is well, it is what you would get if one of the variables was 0. So I'll go back to the first slide to show that this is really indeed the case. If or is this obvious to everyone? I mean, I can't read the room right now. You're all black. But is this obvious to everyone? Okay, maybe I'll go back. So this is like Sn0q of modulus q. I'll go to the first slide. So this is the case when one of these variables is 0. So you only are summing, let's say, this one is 0, let's say. So you have just am over c. But you're not summing over all the a's modulo c because, well, there's still the condition ad is congruent to 1 mod c, so you're only summing over things that are relatively prime to c. I mean, if you were summing over only all the a's in modulo c, then actually the Kloosterman sum would be easily calculable, but it's not. So, well, it's not too hard actually. This is the Ramanujan sum, but it's an explicit sum. There's an arithmetic part in it. There's a relatively prime condition, but it's simple, and it's a Dirichlet series in these exponential sums, where you're summing over the modules. Okay, so I'm going to tie the study of Ramanujan sums and divisor functions to modular forms and Eisenstein series. So this is going to be somewhat quick, and we won't need the full, like you won't need to understand the next 2 slides or 3 slides, I don't know, fully. Yeah, this one is just, I'm going to say the word modular form, and therefore I want you to maybe have a understanding. So this is one instance of modular forms, or automorphic. They're also called automorphic. So, but if I say modular, then it needs to be holomorphic. It is a function on the hyperbolic upper half plane. So it's on the upper half plane, which is just complex numbers with imaginary parts greater than 0. There is the geometry of the hyperbolic. There's the hyperbolic geometry on it. There's a metric with that. It's a model of the hyperbolic geometry. There are isometries of this plane, and those isometries are given as Z goes to AZ plus B over CZ plus D. So these are the Möbius transformations, and they're isometries of the plane, and holomorphic modular forms or automorphic forms in essence are functions which be on the upper half plane, which behave understandably with respect to these isometries, and with respect to these discrete group of isometries, actually. By the way, can you all see like the side of the plane, or are you seeing? I'm not really sure what I'm sharing right now. Can you see just the screen, or do you see your faces on the right-hand side?
We see, I guess.
You see.
I mean,
okay,
it depends
you see the whole page.
Yeah.
Okay.
It depends also, I guess, the person who wanna keep it or not.
Oh.
But we see your slide and cursor.
Okay. Okay. So, yeah, I mean, this is the point is that this could have been just SL2Z. There are various parameters you can put. You can put a level here, which is like you're not taking this condition on every element of the group, or you're introducing this K, it could be 0. There are various things you can do. And this also, you can even form a Dirichlet series out of the Fourier coefficients of F and form an L function with it. It satisfies the functional equation, and it is supposed to satisfy the Riemann hypothesis. You expect this, and also the Lindelof hypothesis. And the Lindelof hypothesis for this L function would be a consequence if you assumed the Riemann hypothesis for this function. So this is a general concept of a modular form. How would we have a modular form? By the way, what is this gray thing that I wrote here? This gray area is a fundamental domain for this discrete group of isometries. So it's like, imagine in the plane, if you have a parallelogram, and instead of this being the hyperbolic plane, this is the usual plane, and my group of isometries is like just translations, z squared, translations to the left and to the right, and they tessellate, they tile the whole plane. So this is something similar here. So this is so in that case, the parallelogram would be a fundamental domain, fundamental region. Here, this thing I've written is also a fundamental domain of so when you tessellate this gray region with hyperbolic translations, you obtain the whole hyperbolic upper half plane. Okay, so how would you, and again, you can stop me anytime, and then please tell me if you don't understand it or want me to be slower or faster. So we have
actually, Mehmet, I want to ask something like in the previous slide. So in the last line, there is this gamma SF, and how F is on the
F is only there for by virtue of kappa. So only the weight, or like only that aspect of it is infinite. So to say.
I see. Like
so this is the infinite part of so this is a
weight of the modular form you use.
Yes.
Okay.
Yes. The weight of the modular form is the only thing that shows itself in the infinite gamma factor. And you have here two gamma factors, which indicates that, and also like if I didn't write it down, but this also has an Euler product expansion, and the Euler product for each prime, you would actually have a degree 2, like instead of 1 minus 1 over p to the s, you would have 1 plus minus, I don't know, something over p to the s, and then 1 of plus something over p to the 2s. So it would be a degree 2 polynomial in p to the minus s over there. So it would be like a two linear factors. So in this case, we have two gamma functions as well. This is kind of because these are modular forms on GL or SL2. And Eisenstein series is a modular form on SL2. So we want to create a function which is kind of invariant, as you can see the F here. It's kind of, we want to create something which is kind of, if kappa is 0, it is invariant under a group of isometries. So one way to create an invariant function would be to average. So like if I have E of gamma prime Z, then this would be the imaginary part of gamma gamma prime Z, and gamma gamma prime, as you run over gamma, will actually run over everything. I'm not running averaging over all SL2Z. That is because this gamma infinity, which I have to introduce what it is. This gamma infinity is the set of translations. So imagine the action was AZ plus B, CZ plus D. So if you apply it to the 1 n 0 1 here, it would be Z goes to Z plus n. So it's translations by integers to the left or to the right. And the point about translations is that they don't change the imaginary part. Like if you're translating to the left or to the right, like this is not changed. So if I were summing everything in SL2Z, then I would keep repeating the same number infinitely many times, and that would not converge. And also, I don't need to average over gamma infinity because it's already invariant under gamma infinity. So I'm averaging over what's left. So this is the summation over cosets, the left cosets of SL2Z. Okay. And this for any fixed S, this is straight up invariant. That doesn't even have a K. It's not holomorphic, but as I told in the previous slide, it's not holomorphic as a function of Z. So this is an explicit version of this, like with C and D, relatively prime, and this is the imaginary part of gamma Z to the S. This is what you get. And so I want to calculate the Fourier coefficient of this Eisenstein series in two ways. One of them will give me the Dirichlet, the divisor sum function, and the other one will give me a Dirichlet series in Ramanujan sums. Yeah. So one way of doing this would be to get rid of this greatest common divisor function condition. This is a typical, like for those in analytic number theory, people do this all the time, but I'm just going to skip it and jump to the point. The nth Fourier coefficient of the Eisenstein series is given as such. It's too explicit for my purposes at the moment, so I'm just going to write it as a star asterisk. I'm not writing everything down. So it is sigma, the divisor sum function over zeta 2s. The second point is, so this is not that hard to do. It's an explicit computation, but I'm not going to do it very. Like I'm not going to be. So if you didn't understand the first part, it's okay, is what I'm saying, because I didn't explain it. I'm just writing the formula. It's a somewhat easy to get that. The second one is also easy to get, but I'm going to be doing it like calculating it slightly more in detail. So what I do is write the Eisenstein series as a sum over SL2Z. Just this is the definition of the Eisenstein series with imaginary part of gamma Z. Write it instead of a single coset of gamma infinity as a double coset of gamma infinity. So to the right of gamma, I'm separating the 1L01 part. And maybe it will be clear why I do this in a second. It's so what is this 1L01 acting on Z do? It just is Z plus L. It doesn't do much. I mean, it's a translation to the right. And by a change of variables, x goes to x minus L. That doesn't change the exponential e to the 2 pi I here. That's e to the 2 pi I doesn't change under integer translations. So that changes to, actually it should be minus L to minus L plus 1, but that's not too much of a problem right now. So, oh no, maybe it was correct. No, it is correct. It's L to L plus 1, sorry. So now there is nothing L. There's no L inside the integral. So again, this just tessellates to the whole real line. Okay, so now we have a summation over SL to Z double cosetted by unipotent matrices, the gamma infinities. And the calculation then takes, so remember the previous C and D. So maybe I'll go back slightly to here. So, okay, I'm going back slightly to see that if gamma is A, B, C, D, so we have a matrix in SL2Z, but if you're cosetting, if you're dividing on the left by gamma infinity, this means that it would be determined by well, there's a slight calculation, but it's determined by the bottom row. The upper row is it's just C and D, which are relatively prime, will give me a unique SL2Z matrix. If I divide on the right also by gamma infinity, the thing that changes is that I still have the C and D, the bottom row determining it, but not all D, well, I only have D modulo C. Anything D plus C and D would be in the same double coset. Okay, the next move is to make a change of, so here's the move. I'm doing it back and forth. X goes to X minus D over C. That changes the integral like this, and then I have E of dn over C coming up. And that is summing over all the modulo, all the D's modulo C that are relatively prime to C. That is exactly the Ramanujan sum. And the right-hand side I'm going to ignore. It's exactly the same asterisk there, so I'm going to ignore. So this is how you would get the Riemann, the divisor function, the divisor sum function equaling a sum of Ramanujan sums, a Dirichlet series of Ramanujan sums. So if I'm going to do something almost the same, very similar, with a Poincaré series as my next step. So Poincaré series, is almost the same thing. I'm still trying to create an automorphic form. These are centrally important in the study of automorphic forms. Well, you'll have to trust me on that. They are used all the time in, for example, the inner product of a Poincaré series with any other modular form would give me, for example, this pH. If I take an inner product of pH with f, I do get the hth Fourier coefficient of f. And these Fourier coefficients of modular forms usually encode arithmetically significant numbers in them. So Poincaré series are important. If we have established that, it's almost given by the same thing. With instead of just imaginary part of gamma z to ds, I'm averaging e to the 2 pi I hz, which is again invariant under the left translations by integers. So again, I can switch to a double coset summation. But now instead of just y to the s, I do have this extra factor here. And if c equals 0, I'm going to use this identity. And I wouldn't say this if it weren't important. So with this identity, what can I do? It's this a over c will give me the ha over c. And again, a change of variables, x going to something, will give me an nd over c. And I have a Kloosterman sum here because a and d, they're coming from this 2 by 2 matrix with determinant 1. This is coming from SL2Z. So AD minus BC is, sorry. AD minus sorry, AD, okay. AD minus BC is congruent to 1 modulo C. So this is indeed a sum of Kloosterman sums, a Dirichlet series of Kloosterman sums. So hence Kloosterman sums enters the study of automorphic forms. Okay. And the integral I'm going to ignore for now, it's just asterisk. So, but what I'm saying is that this Dirichlet series in Kloosterman sums is appearing right there in the Poincaré series, and this is a general feature. It will happen in higher rank, like SL3, SL4 Poincaré series. So what did I do? What was important about this AZ plus B and CZ plus D? Like, what was important? So many of you probably have seen this in complex analysis, for example. You might have seen this. I don't know if you have, but you might have seen this formula. But this is a manifestation of the Bruja decomposition, the BWB decomposition of SL2. Why? So what is the BWB? So here B is the set of upper triangular matrices. It's, in the case of SL2, it's the Borel subgroup. W is the Weyl group. In this case, it's the group of permutation kind of matrices. In SL2, things are very simple. There are only 2 elements in the Weyl group, the identity and the only reflection. So using this BWB decomposition, we can also cap that with SL2Z, like take the intersection and get a decomposition of SL2Z. So on the one hand, you would have BIB. So these are upper triangular identity. So this is just upper triangular SL2Z matrices, which means it is the gamma infinity. It's the upper triangular SL2Z matrices. So these are characterized by the fact that they have the lower left corner equal to 0. So it's like a 1 plus minus 1 and 0 plus minus 1. And the other cell, it's called the big cell, is characterized by the fact that the lower left corner is not 0. So it is the BSB group. Sorry, cell. It's like a set. It's a set of, it's a double coset. Okay. So, and for ABCD in the big cell, the decomposition, this decomposition that I've written, like A over C, 1 over C, CZ plus D, that is related to this factorization. So this is the BWB factorization. So I start with a unipotent. So B is the upper triangulars, but I can make them unipotent. So I can concentrate my diagonal here. So here it's very explicit. 1 A over C, 0, 1. So this is the unipotent. I have the W element, the S here, the diagonal element, and then another unipotent element. So this is an explicit version of the BWB decomposition, which is where the Kloosterman sum is coming from. So this is what we had. We had e to the 2 pi I n A over C, so the left unipotent, and e to the 2 pi I m D over C, so the right unipotent. So this will be a summation over the double coset. So we can interpret the SL2 Kloosterman sum as a summation of matrices in the big cell, double coseted with a particular lower left entry. So I'm going to finally enter the higher. Yep, I have time. Okay, any questions? So I'm entering SLR. So what would a Kloosterman sum mean in SLR? So I'm going to define it now. No questions. So I have the group of unipotent matrices. Let's call that UR. So one's on the diagonal, upper triangular. Any Weyl group element, take that from SLR. So in the case of SLR, the Weyl group is, well, it can be seen as the permutation group on R letters. So in SL2, it was permutation on 2 letters, so you only had the identity or the transposition. But, well, in SL3, you will have 6 elements more. So you'll have 6 Kloosterman sums. Some of them will be trivial. The identity element will. Oh, maybe I should show you that. In here, in the Fourier expansion, you can see there's a delta term that is coming from. Oh, sorry. This term here is coming from the small cell. The other one is coming from, for each C, for each lower left corner. This is you have sliced the big cell into separate C's, and the Fourier expansion of the Poincaré series reflects the Bruja decomposition in this way here. So we will have 6 many. In the case of SL3, we will have 6 many Kloosterman sums. Some of them may be trivial, and then therefore the Poincaré series Fourier expansion on SL3 will have 6 many terms. Some of them will be. Anyway, so this is just a notation for the diagonal, since we're dealing with SLR, determinant 1 matrices. They will have to be like all the terms multiplied has to give you 1. So this is the double coset given a central element, C. This is what you would. This is the double coset. Sorry, they're given a diagonal and given a W, given a Weyl group element. This is the double coset of matrices, where the left unipotent and the right unipotent vary over all unipotents in Q actually. So this would be not URZ, just URQ rationals. And take a super diagonal character. What do I mean by that? So I give the 3x3 example here. They're indexed by 2 integers, and it is, so you take a unipotent matrix, and then you say n1 times the super diagonal element here, and n2 times u23, so the super diagonal element here. So these are all the characters that you can have. This is very explicit, and the Kloosterman sum is thus defined. So this is a summation over matrices of, so given a W, given a C, so C is the modulus, it's moduli, actually there's more than one element. In SL3 there will be C1 and C2 for, you take the URZ double cosets, and you factorize your A into a left and a right Kloosterman sum. You factorize it according to the Bruja decomposition. And you have the left unipotent and the right unipotent. The left unipotent you put into a character, psi m, and the right unipotent you put into a different character, and you sum over all the matrices in this double coset. So this is the this is the definition. It's not very useful unless you're using some abstract properties of it, but it's not explicit at all. I mean, whatever the hell this A factorization is, you just put it here. But I mean, it's not like it's not like the SL2 one, where I have a single parameter A modulo C run over all the terms modulo C, and D is completely determined by that with A inverse modulo C. And I can express the whole sum with a single parameter, A, running over modulo C. So I want to do something similar here. I want to have maybe more than one parameter run over various moduli. It can be more than one, and we will have 3 actually. And write this more explicitly, and maybe in the way C factors of SL2 inside this sum, SL2 Kloosterman sum inside this SL3 Kloosterman sum. So the hardest one is the long word. And I'm going to do that. The other ones are actually better understood. This is where the roots enter. Well, they don't enter very substantially, but they do enter the picture. So SL3 has a root system, and they have simple roots, alpha and beta, as can be seen in the picture. What is more important for our purposes is that for each root, there's a simple reflection that's associated to each root. And as matrices, we can express them as matrices in SL3. We can express them as basically the same as S in SL2, but in the upper left corner, and S beta the same, but embedded in the lower right corner. So I would like to write an element in, oh, by the way, this should be W0, omega 0. So this is the long word of the Weyl group. I said there were 6 elements. The reason I'm saying long word is that every permutation can be written as just like a product of these elements. And these products are, well, there's a reduced one, there's a smallest one, and that's the length of the Weyl group element. In this case, it's 3. You can only write it W as, well, you can write it either as S alpha, S beta, S alpha, or S beta, S alpha, S beta. But in any, you can, there's a fixed length. They're both 3. And given one reduced word decomposition, I would like to write it as a product of 2 SL3 SL2 matrices. So I have a root alpha, or like a simple root alpha, and then I want to embed a 2x2 matrix into the upper left corner. So given the second factor here, beta, I want to embed my 2x2 into the lower right corner. And again, given the alpha, I want to embed it to the upper left corner. Why would I expect this to lie in BW0B? Well, the point is, so each of these 2x2 matrices here, so this is actually living in the upper left block. This is just a 2x2 matrix. So it has a decomposition of the form, so let me go back, just like the bottom in here. Like we can apply this decomposition, factorization. And this factorization has the S in here, which if lying in the upper left corner, it means that it is just S alpha. So if I do the factorization on the first matrix, I do have a S alpha in the middle. I have an S beta in the middle. I have an S alpha in the middle. So if I rearrange things, which is not trivial, I mean, it's not that you can't do it freely, but if you do rearrange things, what you can get S alpha, S beta, S alpha in the middle. So you can have W0 in the middle. So this will be an element of BW0B. So it will be an element of the big cell in SL3. Hopefully the rest of the matrices will also be like a unipotent, and like unipotent on either side. And then we have 3 factors, 3 moduli, D1, D2, and F. And also these factors satisfy this x2, y2 is congruent to 1 modulo D2. So there's like 3 parameters that I can run over. Any questions here? Like x3, y3, y. Unfortunately, they're not, or maybe fortunately, I mean, it's not that simple in the sense that it's they're not totally independent of one another. So there are relations between them. But in any case, we can factorize them, or we can hope to factorize them. And it is true. Given a matrix A, it has the long word has a decomposition like this. This is called the Bott-Samuelson decomposition. Given an integer matrix, and also if you want to keep everything else as 1, you don't necessarily get the same matrix, but you get something in the same double coset. And assuming this, now we have two sets of coordinates. One is the coordinates coming from these x's and y's and f's and d's. And the other one is just the coordinates of entries of A31, A32, that sort of thing. And you can pass between one another. For example, F would be obtained by the GCD of either the lower left corner and the lower, well, the next one, the bottom row, first two elements, or the lower left 2 by 2 minor and this minor. Oh, and by the way, just like the big cell, the BWB set, this algebraic set, is in SL2 was characterized by the lower left corner not being 0, the C not being 0. In 3 by 3 case, if I take the long word, the BW0B is characterized by A31 not being 0, and the lower 2 by 2 matrix minor not being 0. So that, and the other Weyl group elements have different characterizations. And we have numbers. Like we have the D1 can be characterized as this, D2 can be characterized as this, and you act A on the exterior algebra of the standard basis elements. You get X2 if you like. So there are two ways you can do this. Like if you assume the coordinates of A, you get a minor. Like the entries of A, you get a minor. But if you look at it from the lens of this factorization, this product, so this is, you act A on E1 wedge E2, and then you look at the E1 wedge E3 component of this product, you get X2 times F. Thus, using this and many other like exterior algebra calculations, you can get all of them, like X1, X2, etc. And using these coordinates, you can write the Kloosterman sum in parameterized form. And this is the formula. So what is it? So I said there were three parameters, like D1, D2, F. So instead of the two parameters, what you do is that we had the omega WC. And from the omega WC, that's a set. We slice this algebraic set into pieces, into strata, if you like. That is parameterized by F. And I get, this is, I'm sorry, I thought there would be more difference between this S and that S, but this is a fancy S. So this is the fine Kloosterman sum. This is a finer substrata of the big Kloosterman sum. So basically, this is the same sum over a smaller set. Those with GCD equaling GCD, this GCD, those elements, sorry, those elements in the big cell such that this GCD is equal to F. That is my small set. So that means I fact. Why is this? Okay, sorry. Okay. So I get the Kloosterman sum decomposed into F. Each of these F can be expressed as F times a product, a sum of a product of two classical Kloosterman sums. These S, this is the classical SL2 Kloosterman sums. So here's that was what I hoped would happen, and it did happen, is that we get the Kloosterman sum times another Kloosterman sum. So these are given by, so this is, you notice this D1, this Kloosterman sum is coming from the first matrix in this triple matrix factorization. First matrix in this triple matrix factorization, and this is coming from the other one. And the summation over F, well, that's the middle matrix. There is a condition here, which is slightly unfortunate, but it is the truth. What can I do? I mean, this is what nature gave us. And here, this NY and MX are given as these conditions. And this M2D2 congruent plus N2D2Y wouldn't be equal to 0 modulo f unless this GCD condition was satisfied. So this, because this y is relatively prime to f, this is the only way. Okay, I started 5 minutes late, so I have 5 minutes. So that's okay. I can do it in 5 minutes. I know I hate people when people say this, but I have 5 minutes more stuff to say.
Please.
Don't,
feel free.
Don't look at the number of slides. I don't have to show every slide. It's okay. So this is explicit, is what I'm saying, and maybe let's show that it's explicit. Here I take my Kloosterman sum. The first one is a factor. It's a decomposition into the various f. So you would have p. So what are the GCDs of what could divide the GCD of p squared and p? Well, it could be f could be either 1 or p. So that's the decomposition. The first one you can just calculate like from the formula in the previous page. It's 0. The second one, well, it could only be, you do the calculation and it's rather simple, p times p minus 1 times s11p. So you can be quite explicit that this whole thing ended up being p times p minus 1 times s11p. Here's another example, and this is quite nice. Like, it simplifies quite a bit when the only choice of f is 1. So when d1 and d2 have GCD 1, so the only choice of f is 1. By the way, this particular example was already known, but I mean, I wanted to include it because, so this last line is not new, but I mean, it shows like the structure of things a little bit better. So it's a product of two Kloosterman sums with 2 moduli, not 3 because the f is 1, where the modulus of the first factor shows up in the twisting factor of the second one, and the modulus of the second one shows up in the twisting factor of the first one. These are two classical SL2 Kloosterman sums multiplied. Oh, sorry. And you get why? Oh, okay. Sorry, it keeps moving out of my, like, anyway. All right. So, and I said I would have to. I said I would do something about the Ramanuja, the divisor function in the in D3. I said I would have a formula for D3. So this R is just shorthand notation for the Ramanujan sum, but I didn't want to write everything like this. So we have an explicit Ramanujan sum, and we consider the double Divisor series. So this is exactly the analog of what we had in the 2x2 case, where we had a Q here, and we were summing over Q to the S. Now we have two factors, C1 and C2, so it's a double Divisor series, C1 to the S1, C2 to the S2. Instead of one zeta factor, we have 3 zeta factors, which sort of shows that we must have been looking for 3 moduli to start with. So instead of 1 zeta S, we have 3 of them. So that gives, so that simplifies if, oh, I didn't write, well, that's, okay, so here we should have n, RF of n. Sorry, I forgot that. The point here being that we have here a triple Divisor series expressing this sigma function generalized to SL3, being writable as a triple Divisor series of exponential sums. This is the Ramanujan sum, so modulo f, but there should also be like a twisting factor here. Sorry, I don't know how I missed that, but anyway, there should be something here. So this is an exponential sum. So again, we have an exponential sum explicit. This is the Möbius mu function, explicit exponential sum, and you have a Divisor series of it. And what is the left-hand side? Well, the left-hand side, I didn't define it yet, but it is given as number of ways of writing n as a product of 3 numbers, where it's like the divisor sum function. but now we have 3 factors. And if S1 and S2 are 0, then you do really get the number of, so this is just 1, so we're just summing 1. So this is just the number of ways of writing n as a product of 3 numbers. And this is exactly what would show up in the 3rd power of the Riemann zeta function if you wrote it as a Divisor series. So what are advantages? What are our advantages? First, you might hopefully have expansion of D3n. So these are the kind of things that would show up in analyzing the 6th moment of the Riemann zeta function. So even this, by the way, the asymptotics of this, just for h equals 1 even, is not known. So there's at least like the first step I would do is to try to, well, one thing you can do at this point is to expand this in terms of an exponential sum with n plus h in it, a series of exponential sums, and maybe have a hope at the 6th moment of the Riemann zeta function. This I'm going to skip. This has the fact that it is writable as a product of 2x2 matrices might have various implications if there are other factors that behave multiplicatively and also behave well with 2x2 factors that are like very easily explainable in terms of 2x2 factors. And I'm going to skip this maybe. And the third one is it actually generalizes quite well to gamma 0 n. So all this we did with SL3Z matrices, and I didn't even tell you what gamma 0 n was. Oh, no. What gamma 0 n was? Do I have time? No. Okay. But gamma 0 n is the group of matrices where the lower left is divisible by n. Maybe let me go back slightly a little here. So F is the GCD of A31 and A32. These two elements being divisible by n is exactly the same thing as F being divisible by n. So that's a complete characterization of gamma 0 n. Gamma 0 n is described by these two elements being divisible by n. So what you would have is basically this Kloosterman sum would still be written as a summation over the F parts, but only those F which are divisible by n would show up. And that's all. Thank you very much. I'm sorry I'm late, but hopefully not too bad.
Thank you very much, Mehmet, for this very nice talk. And
thank you.
Yeah.
Any questions?
Yeah, any questions, remarks? Please unmute yourself and ask your question. Yeah. So actually, I will ask one question. On the example of this long word, you did one example. And then writing this A, capital A, there is this order for 2, 3, 1. Yeah, I was just
1, 2, 3, yes.
Yes. Yeah. Why is it like this?
Okay, let me try to. It has been a year, so let me try to remember.
I mean, I was just curious if there is some. Yeah, I mean, like
there is a logic. There is a logic. It's there was a logic, or at least. I forgot now, but the numbering seemed to make more sense. If honestly, I forgot now. Okay. But it did make more sense in this, like within the calculation, to order them this way.
Yeah, maybe.
I think the reason
anyway,
was,
in the next slide, it was like 1 till R, I guess. But just like if there is some sort of structure, like combinatoric structure on these, like
there is.
Decomposition.
Yeah, there is. The long, but honestly, I forgot now. Like
Okay.
there certainly is, but
Curiosity, no worries.
yeah.
Yeah.
This gives an ordering. This like a reduced word decomposition does give an ordering of the positive roots, and this, like this alpha, beta, alpha, these all have to do with this ordering of the roots.
Root system. I see. It's like okay.
But like I don't remember it well enough right now to be able to say why it was this. I do also remember now what it would be in a SL3 case, but like
fine.
Yeah. So if you do the ordering of the roots, like sorry, this is just simple roots right here, right? Like alpha, beta, alpha. But it does there is an ordering of, so when you move things around, the middle factors, this one has a D1 here, right? I remember now. So,
great.
Okay.
Actually, I don't have so much idea, so whatever you say, which is kind of making sense, would be meaningful for me.
Do you remember, where is it? Okay, so this is D1 on this part, there's F here, and then there's D2 here, right?
Right.
And the way I want to write this in the end is left unipotent, W0, a diagonal matrix, and right unipotent.
Right.
So you factorize each of these into the 2x2 Bruja decomposition. So these are your tiny Bruja decompositions with, and what you have is a D2 1 over D2, F 1 over F, and like a D1 1 over D1 in the diagonal parts. And when you combine all of them into like one big diagonal, they correspond to like you would have a D1F 1 over D2 over D1 and then 1 over D2F, in the sense that like the diagonal follows the order of, so I wanted to have the D1 associated to the first root, like the alpha root.
Yes.
I wanted to have the F.
Now, yeah.
I wanted to have the F associated to the alpha plus beta root. So that was like in the one in the middle here. And so it would be F 1 over F on the other side. And then I wanted to associate D2 to the beta roots. So if I order my simple roots, I want to have D1, D2 follow the simple roots. And this is the one that gave me that.
Thank you. Any other question?
I have a question. Hi, Mehmet. Can you say more? Can you say more about the average of the D3 and D3M plus H?
Yes.
In your last slide.
So I think you know very well that this is the kind of thing that would show up in the Riemann zeta function sixth moment. And so what could I do to study this? One thing I could do is try to this is an additive factor, and I don't like the additive factor here. Why don't I like? Because this is a multiplicative function, and inside the multiplicative function, I have this additive factor. So if this was D2, D2, like the fourth moment, what Motohashi does in studying the fourth, I think Motohashi, and maybe other people too, in studying the moment is replace this as with sigma sub-0 of n plus h. And write that sigma as a sum of Kloosterman sums, sum of Ramanujan sums, sorry, like a Dirichlet series in Ramanujan sums. So maybe I go to the first page in doing this. Where's the formula? Here. Here, I would have an n plus h. But this is an exponential sum. So I would have an n plus h in this factor in here. And the exponential finally behaves well with respect to addition. I can have the e to the 2 pi I an over q times e to the 2 pi I ah over q. Now I have separated my n and the h. There is a cost. I have added a huge sum over q. So it's not that simple anymore, but now I have so many variables I can do harmonic analysis with. Like I can do, I don't know, Poisson sum this, like integrate that, like I don't know, like take Fourier expansions in many variables. Well, I don't know, actually mostly Poisson, but like do the Poisson summation formula in some of the variables. So this is what Motohashi does, right? Like, so this was the whole impetus in trying to come up with writing the Kloosterman sum, was to get the same, this formula for, it was my impetus, to get the same for Ramanujan, sorry, for D3. So where I can write this triple version of this, the triple summation version of this instead of the double, in terms of an exponential sum where I can finally separate the n and the h because of the exponential. So that's the goal. Well, it's not that simple actually. So I couldn't really get it to work, but I didn't try that much is also the other thing. So to try to separate this n and the h and finally get something about this exponent. I couldn't, but I mean, it would be a first step is what I'm saying. Like it would be my first step in trying to separate the n and the h here.
Yeah. Thank you.
Thank you for asking.
Maybe more questions? It seems not. No. Thank you for coming today also, our fifth talk of Üçgen, and hope to see you next week. We'll stay in the room like 10 minutes or so. Please join us if you wish. It's like, yeah, kind of coffee break or something. Yeah.
I was wondering if you were gonna take me to dinner.
Just a sec.
We ordered food for you. It will come soon.